Have you ever heard of silver nanoparticles and what they have been used for? Silver nanoparticles can be found in many aspects of our daily lives but often go unnoticed. In this video, we will discuss how these elusive particles are made using capping agents. So what are silver nanoparticles? They are tiny particles of silver metals with diameters ranging from 1 nanometer to 1 micron and typically have a wide variety of geometries such as cubes, rods, and faceted structures, which are essentially structures with several flat surfaces. These nanoparticles have several applications in the biomedical and pharmaceutical industries, as well as in solar cells. Now that we know what they are, let us look at how they are synthesized. There are generally two methods of synthesizing silver nanoparticles, namely the template method and in solution using capping agents. In this video, we will discuss the method involving capping agents. In the use of capping agents, they are usually mixed with a silver precursor and a reducing agent in solution to form silver nanoparticles of intended shape and size. Some capping agents can also be used directly with pre-synthesized nanoparticles. Before we go into the finer details of capping agents, we must first understand the purpose of capping agents in silver nanoparticle synthesis. Let us now take a closer look at what occurs within a solution of nanoparticles. Here we have some silver nanoparticles in solution. In the absence of capping agents, these particles spontaneously aggregate to form larger particles of irregular shape and size. This is undesirable as it affects their physical and chemical properties, leading to complications in subsequent applications. As such, capping agents are used to stabilize these nanoparticles in order to control their shape and size. In the synthesis of silver nanoparticles, commonly used capping agents are small organic molecules, polymers, dendrimers, cyclodextrins, reducing agents, and surfactants. These capping agents stabilize the nanoparticles via various modes such as electrostatic interactions, hydration forces, depletion, van der Waals forces, steric hindrance, or a combination of the above-mentioned modes. In this video, we shall discuss only steric hindrance and electrostatic stabilization. In electrostatic stabilization, an ionic salt is added to stabilize the nanoparticles. This involves the use of an ionic salt such as sodium borohydride and a silver precursor in solution such as silver nitrate. In the case of sodium borohydride, it also serves as a reducing agent, thus eliminating the need for further addition of reducing agents. Let us now take a closer look at what occurs within the solution. Sodium borohydride reduces silver nitrate to form neutral silver atoms which aggregate to produce silver nanoparticles. The borohydride ions in solution then proceed to absorb onto the surface of the aggregated silver nanoparticles, thereby imparting a particle surface charge. As such, further aggregation of silver nanoparticles is prevented via stabilization through electrostatic repulsion of negative charges, thus allowing them to form in a regular shape and size. Moving on to the next method of stabilization. Polymers are one of the several types of capping agents that stabilizes nanoparticles via steric hindrance. Polymers such as PVP are added to a solution of nanoparticles after they have been formed through the addition of a reducing agent to a silver precursor. Let us now take a closer look at what occurs within the solution. In the solution, we have silver nanoparticles that have already been formed. Upon addition of PVP, these polymeric units interact with the silver nanoparticle via the pyrrolidone group, while the hydrophobic alkyl chains extend into the solution and interact with each other, thus forming a polymeric cage around the nanoparticle. Through this mechanism, PVP prevents further aggregation through steric hindrance, thereby allowing the formation of nanoparticles of regular shape and size. Now that we have discussed the basic mechanism of some capping agents, let us see why it is important to have control over the size and shape of the silver nanoparticles. Firstly, the size and shape of the nanoparticles are correlated to their localized surface plasmon resonance, which is essentially responsible for the physical and chemical properties of these particles. When they are exposed to electromagnetic radiation, their conduction electrons become excited and exhibit collective oscillations in resonance with the incident wave. This phenomenon influences the wavelength at which light is absorbed and scattered, since absorption is dependent on electronic behavior. Due to this reason, the wavelength of light absorbed by the nanoparticles vary with their shape and size. thus affecting the color of their solutions. As such, the shape and size of these nanoparticles play an imperative role in their applications. For example, since solar cells absorb and convert light into electrical energy, the wavelength at which light is absorbed can affect its efficiency. Also, since the localized surface plasmon resonance effect influences the thermal properties of these nanoparticles, the geometry and dimensions of these particles are crucial in its applications in the biomedical industry, such as photothermal therapy. Capping agents are critically important in the synthesis of silver nanoparticles, and variable applications of these agents heavily influence the geometries and dimensions of these particles. As such, possessing a good understanding of its working principles provide great insight to understanding the many applications of these nanoparticles that we may overlook in our daily lives. Thank you for watching, and I hope that you have enjoyed this video.